And welcome back, Mindsetters. I hope you had a nice little break there. You went and did whatever you had to do, so now you stop fidgeting and pay attention. Make sure you have your pens and pads out and you're ready to make notes, because I'm going to continue with the rest of the session. And this is where I hand straight back to Mr. Eugen. Eugen, take it away.
Thanks, Ty. Guys, well, the first session was power-packed, lots of information, and I know this is the best part, and you guys like experiments. I'm doing a very simple experiment this afternoon. I've got 3 different soil samples, and we're going to establish their water holding capacity. What I have in front is we've got 3 samples, A, B, and C, and we've got a funnel, and in each funnel I've got a little piece of cotton wool. I've got a funnel and a conical flask labeled A, B, and C for the respective samples. And what we're going to do basically today is we're going to put in equal amounts of samples into each of these beakers, each of these funnels. We're going to add in equal amounts of water. We're going to allow it to run through, and we're going to measure the amount of water that comes through. So the aim of this experiment is to establish the water holding capacity of the different soil samples, and we would then make a call as to which would be the best soil sample to plant or to cultivate in. So let's get busy. Okay, so if we look at the first sample, we can feel the texture of this. If you guys come closer and you have a look, you'll see that it is not as sticky as soil. It's very fine particles that do not stick onto my fingers. I'm going to pour that into conical flask A. Okay, I'm going to do the same for sample B. Sample B feels very fine, small, tiny particles, and you can see them drop very easily like salt from my hand. And no guesses for guessing where this is from. It's probably from a river, from a lake, where the soil particles are very fine. I'm going to pour that into the second conical flask, and we move on to the last one. This is a sample that I've taken out from my garden, and if you have a look at this here, you'll see that it's dark in color, lots of particles in there, some dried roots and leaves, and this essentially is very loose and granular, something that I think would be ideal to grow in. So I'm going to pour that into the last beaker. Okay. To each of these samples, now we've added the different soil samples. To make this experiment a fair experiment, we've got to add equal amounts of water. So to the first sample, I'm adding 40 mLs of water, and I'm going to allow that to run through. And I want you guys to watch carefully, and you're going to see the water percolating or dripping down gradually. Okay. Whilst we focus on that, I'm going to fill the next beaker with another 40 mLs of water, and that's going to go into sample B. And watch this, guys. We're going to expect lots of water to run in that. And the last sample, again, 40 mLs of water into that. And here you go, 40 mLs into the last sample. Okay, I'm going to give it a gentle stir with the glass rod. Likewise for each of those samples, a gentle stir to make sure that we facilitate the movement going through. Okay. Now if we watch this. Okay. So here we've got very little movement, very slow drops dropping through. Here in the second sample B, we've got water coming through, probably faster than sample A. And in the last sample, we've got water dripping through very easily, but not as fast as in the second sample. Okay, so we're going to allow this to stand a little while, and in about a few minutes, we're going to look at the different water samples and measure the volume in each of these samples. Okay, before we move on to the next experiment, I want to show you guys what litmus paper is and how to test the pH of different samples. Here I have with me, I've got three Petri dishes labeled A, B, and C, and we're going to take a drop out of each of these soil samples to establish the pH of the water in those samples. And by establishing that, we would know whether that soil sample would support life based on the pH level of that. So we said that pH was measuring how acidic or alkaline a substance or a medium was. Today we're going to be using LIT. We're going to be using a universal indicator paper. And this is a universal indicator paper because it can measure pH from 1 right up to pH 14. Okay. We also have different types of indicators. An indicator is basically anything that can tell you the difference in pH of samples. Here we have red litmus paper, which can also be used to determine whether a substance is alkaline or acidic. And we also have blue litmus paper, which could also be used to determine whether the substance is acidic or alkaline. Whilst I was on my way, I stopped along a mine dump and I picked up a soil sample, and I was very keen on establishing what the pH of this soil sample is. So along with that, we're going to establish what the pH of this soil sample is. Okay, so I'm going to add, and this will be quite interesting, guys, and often you notice that whilst you're driving along, especially in Gauteng, you notice that there's lots of mine dumps and they're white and very little plant life on there. Whilst we allow this to continue, I'm going to take my litmus paper from sample A. I'm going to touch it into sample A. I'm going to feel that, okay, we're not going to get very good results in that. Okay, into sample B. I'm going to place that upside down, and into sample C to determine the pH of that. Okay, okay, and obviously the unknown sample from a mine dump. Okay, I'm going to give that a bit of gentle stir. And I'm going to place that right on here. Okay. Here we have a color chart, and this color chart obviously will indicate to us the different pHs. When we look at this color chart, we've got pH different colors from 1 all the way to 11. 1 being very acidic and 7 being neutral, with 11 being very alkaline. So let's look at these samples and determine what the pH of the different samples are. If we look at A has a pH of about almost 7. So this is probably slightly neutral to alkaline. If we look at sample B, slightly acidic. Sample C would be again slightly, I would say very close to being neutral, maybe slightly alkaline, on the border between 7 and 8. So this would be almost neutral. And interestingly, let's look at the sample that I picked up at the mine dump, and this appears slightly, is it close to orange, guys? I would think number 4, which would be, yes, it would be acidic. And but naturally we would know this because from your mine dumps you're going to get lots of acidic effluents coming out, and these drain out into the landfills, and that is why this appears acidic. Okay, let's get back to the water retaining capacity of our different soil samples. I'm going to stop that there, and I'm going to measure the amount of water in each of those samples, and I want you guys to help me with this. Okay, so we're going to very quickly measure the amount of water in that. So that's the amount that has come on through from A. I'm going to put that back into A. We're going to look at B in a while. We're going to look at C as well. Okay. Right, so here are your results, guys. Here we've got sample A, which has a volume of about slightly less than 20. If we look at this very carefully, it's about 17, 18 mLs of water. And we initially, if you remember, we added 40 mLs of water. So you can do your maths and you can work that out. 40 minus 17 would be 23. So we've got 23 mLs of water that are still in this soil sample. Lots of water in there. If we look at this sample B, we've got about 20 mLs of water in there. So this also has passed a lot. So we've got still this draining through, and probably by the end of the day we would have all coming through. If we look at sample C has 30 mLs of water that have gone through. Okay, if you look at this sample, you'll find lots of leaves and dried organic matter on the top, which would be very rich. Okay, so guys, if we look at the results of this experiment, as to where we are now, you'd see that the different samples have different water retaining capacities, and this would influence the type of organisms that grow. Why? Plants require water, and they require water that is available on the surface. When the roots get deep into the ground, they tap into the water table. And ideally, for plants that are growing in your garden, you need a soil sample that has a moderate water holding capacity and has a very neutral or slightly alkaline pH. We don't want the sample to be acidic, as plants will not survive in the acidic environment. Before we move on to this, I'm going to move this aside and I'm going to simulate an experiment where we see the effect of transpiration. And transpiration, before I do the experiment, is the loss of water through the leaves of a plant. Okay. What I have here is a potometer, and if you guys have worked with one before, you'd know that a potometer is used to measure the rate of transpiration. And we said that plants tend to lose water because plants need to absorb water, and the water is lost through the stomatal pores at the base of the leaves. And this water loss influences the movement of water up to the leaves so that the plants receive their water for photosynthesis. And this constantly happens during the day, and factors like wind, sunlight, humidity all influence the way transpiration, or the rate at which transpiration happens. So what we're going to do today is, I've set up this experiment here, and if you look very closely at this, we've got a calibrated length here that measures the amount of water that will move up the leaf when transpiration occurs. We also have a syringe which is then used to calibrate and to realign the level of water in that potometer. I have set up two experiments for you this afternoon. In one in which I've used a heater, a fan heater. I've got that right here by me, and I had this on for a little while, and I'd simulated dry air in an environment. And if we look at this, after a period of time, we'd seen that lots of water had moved up, and the level of the liquid in there, which is water, I added a color in there so that we could enhance the visibility of that, has moved up quite a bit. So this plant in the last half an hour has lost 10 mLs of water due to evaporation by the heat of the fan, and that loss of water is by transpiration. So we can account for that loss of water by transpiration. In this apparatus here, you'd notice that the movement of water has been very low or very little, because this was kept in an environment that was not influenced by any of the environmental factors. So what we're saying is that in this plant, no transpiration has occurred. So this plant has not lost water by transpiration because there were no factors like humidity, temperature, wind that influenced the loss of water. So guys, is transpiration important? Yes, very important. Plants need to lose water so that the water can be pulled up from their roots, and plants need the water. So this functions as a natural cycle and siphon to siphon out the water from the soil so that it moves up to the leaves for photosynthesis. So transpiration, yes, is very important, and plants need to lose water so that they can pull up water from the soil. The environment in which plants grow determines the rate of transpiration. So we're going to go back for a little break. I'm going to hand you guys over to Ty. We're going to take some questions at the end of the break, and then we're going to look at the results for this experiment on the smartboard. Ty.
Okay, so on that note, Mindsetters, as you heard from Eugen himself, make sure you get those questions in so we can answer them in this last upcoming segment. So make sure you get posting. But on that note, we're going to see you after this break.